Good morning, everyone. Okay, in my previous talk, I talked about the general features of a calorimeter, but without really giving a real example, you cannot understand, how we can make a calorimeter and what type of mistakes we can make if we find it out. Okay, so I'm giving one example, and which is close to my heart. Okay, because I really worked with this calorimeter, which is the CMS calorimeter. It has got essentially two components. As I said, it has got a electromagnetic calorimeter and a hadron calorimeter. But I think my emphasis would be the experience, what I have an experience with the collision data, and why we are not happy with our current electromagnetic calorimeter and the hadron calorimeter. I think you have seen these pictures many times, in the previous lectures. Now, CMS uses essentially two technologies, one technology for the electromagnetic calorimeter and two technologies for the hadron calorimeter. The calorimeter essentially lies between a large tracking device and the magnet. So that is the main region, which really bounds the calorimeter. And the electromagnetic calorimeter utilizes homogeneous crystal calorimeter for its behavior, whereas the hadron calorimeter uses a sampling device because, as I said in the last lecture, you cannot have a homogeneous material, for the hadron calorimeter. But not only that, it uses two technologies. One is it utilizes scintillation, and the other is Cherenkov radiation. So we utilize these two technologies, for the hadron calorimetry. Now, whenever we try to make a calorimeter, everything is driven by some of the things which is required from the given experiment. We know that in LHC, the branch crossing is about 40 megahertz, which means, the branch crossing time is 25 nanoseconds. So we have to be, it has to be fast. We are colliding the beams at about essentially at 7 TeV by 7 TeV. Hopefully we will do it at some point in time. And at such a high energy, there will be lots of radiation which should be there. So it has to be radiation hard. And we do not want to sufficiently increase the cost of the detector. So it has to be compact, as compact as possible. So we try to investigate many materials before we finalize with the choice of the lead tungstate. It has a very high density. It has a short radiation length, and it has got small molar radius. That means, it will contain the shower at a short distance, and also it will be the showers will be narrow in size. And on top of that, it has 80% of the produced light comes within 25 nanoseconds. So it is fast enough, for a detector, so we can try to utilize it. On the other hand, the light output is low, so it needs a large amplification in an environment in a high magnetic field. The CMS is supposed to work at 4 Tesla, but obviously, we cannot operate at the highest possible magnetic field. It operates at 3.8 Tesla, which is high enough. So we utilize two types of devices, to read it out. These are the avalanche photodiode, which is used in the barrel part of the detector, and then we have a vacuum phototriode, which is in the end cap calorimeter. And I'll come to this, why we are choosing these two types of detectors in different parts of the thing. Now, one important thing is that, we see that the light in lead tungsten is typically about 10 photoelectrons per MeV. So it depends obviously on temperature and the diode scheme, but you can see the number of photoelectrons is not very large. Now, you have one detector which is a lead glass, which gives you light essentially through Cherenkov signals. When you can see, the light signals is typically about 1 photoelectron per MeV, which is not so different, than 10 photoelectrons per MeV. It's a large fraction of that is from the thing. So we expect a substantial Cherenkov component in late tungstate. And an experiment was carried out, okay, I mean, by a team from Texas Tech, okay, which tries to measure the component, Cherenkov component using the directional property and the timing structure of the Cherenkov component. Now, what is being done, you had one tungstate crystal and you have got readout on either side. And then we incident particles at an angle and you modify this angle. And you try to measure the signal, and the first thing you see the signals in one of them, okay, I mean, at different angles, they at various, and particularly at the large time, okay, they're similar, but at very small time, okay, I mean, there is a difference depending on the angle. Okay, so there is an angular dependence in one component of the signal. And if you plot the left-right asymmetry as a function of angle, you can see clearly, okay, left-right asymmetry in the thing. And from this, okay, they derived that the amount of Cherenkov radiation is obviously as a function of temperature. And even at the lowest possible temperature which they operated, okay, I mean, it was something about 8 to 10%. Okay, so depending on the method which is used. So I think, okay, I mean, one has to remember, okay, we have a Cherenkov component, okay, and which is not essentially the scintillator. And the second thing which is important is that the light, scintillation light, or even the Cherenkov light is not produced in one part of the scintillator, is produced through the entire part of the scintillator, and the scintillator at the entire part of the crystal, and the light has to travel through the entire part of the crystal, okay, to come to the photodiode. So there should be a light collection efficiency which should be uniform, okay, I mean, along the crystal length. And they tried various techniques, okay, I mean, then they arrived with a technique by essentially depolishing one of the lateral face. The other thing is that you have to worry about at what particular wavelength, okay, this particular light is emitted, and you have to really see that the photodetector which is used, okay, is sensitive to that particular region, okay, and you can see, okay, crystals emit blue-green light with a broad maximum at between 420 to 430 nanometer. So, so that's why, okay, we try to, with this idea, okay, we build the calorimeter in the central part of the detector. In the central part of detector, okay, which essentially covers an eta region from minus 1.48 to plus 1.48. And we put in something like about 61,000 crystals, okay, I mean, in a 360-fold symmetry, so that the accuracy in delta eta delta phi is something like about at the level of, obviously you see, I mean, this how much, 2 pi by 360 is the thing, okay, which is there in both the cases. Now, it is located at a radial distance of 1.3 meters from the center of CMS, and the non-pointing geometry is chosen because we do not want the particles to go through the gaps between the thing, okay, I mean, and so the crystal axis is not along the line of the center, but it is tilted at at an angle of 3 degrees. So each crystal has a front surface of 22 by 22 and a back surface of 26 by 26. And since the crystals are to some extent pointing to the interaction points, we do not have one type of crystals which is made. We have got 17 different types of crystals which is made, okay, I mean, depending on the angle where it is produced. So the crystals are obviously, okay, you cannot put just crystals, but just like that, okay, I mean, they have to be put into some sort of a material, okay, and we have a material called alveolar, which is a mixture of aluminum and glass fiber epoxy structure, and they're put in some sort of a submodule. Now, the normal gap between the crystals is 0.35 millimeters in the submodule. And then once you make a submodule, okay, there is several submodules put in a module, okay, and then I think from module to module separation is about 0.5 millimeter. Okay, this is the thing, okay, which you have to keep in mind. Okay, I mean that there is a gap. Okay, there is a space, okay, where you can lose some energies. So there are 17 pairs of shapes. Okay, one from the forward direction and one for the backward directions. And the submodules are assembled into modules containing either 400 or 500 crystals. And finally, in a supermodule, okay, I mean, which covers, okay, I mean, an eta from 0 to 1.479. So we have got 36 such supermodules which were created, okay, from the barrel crystals. For the end cap, okay, I mean, it was something different. Okay, the end caps, first of all, okay, I mean, cover rapidity range of 1.48 to 3. The important thing is in the end cap is that you have got more particles which goes in the end cap. So obviously it has to be much more radiation hard. And so the all crystals has to be supposed to be more radiation hard, okay, which we could not find such thing. Okay, so all the crystals are made identical. The front face is 27 millimeter by 27 millimeter, and the back face is 30 millimeter, and they're all identical. Okay, I mean, unlike, okay, I mean, we have got 34 types in the barrel, we have got a single type in the end cap. And you can see the length is 220 millimeters, is 24.7 radiation length compared to, okay, I mean, something like close to 26 radiation length in the barrel. I'll come to the reason, okay, why we have made a shorter radiation length in the end cap soon. Now, these are grouped containing 5 by 5 crystals in a carbon fiber alluvial structure. And obviously, okay, I mean, they're grouped in four Ds for the 2 end caps, and each D contains something like about 3682 things. Okay, so we have got roughly 17,000, okay, I mean, crystals, okay, which makes the end cap calorimeter. And again, okay, it is a non-pointing thing. Okay, so the crystals and the supercrystals, they are arranged in a rectangular XY grid with the crystals focusing not at the interaction points, but 1300 millimeter beyond the interaction point. Now, one of the important features of the important consideration in making a calorimeter is that we do not want to see a pi zero decaying to 2 photons and identify them as a single photon. So we want to have an additional requirement in the design is to distinguish the showers from a single photon to a pair of photons coming from decays of pi zeros. Now, the opening angle between the 2 photons in a decay of 100 GeV pi zero is something like about 2.7 milliradian. And if you put a detector something around 3 meters away from the interaction point, the spatial separation between the 2 photons would be something like 8 millimeters. Whereas the Molière radius, which really gives the critical size of the shower, is 22 millimeters. So obviously, okay, I mean, this is not sufficient, okay, to distinguish between them. CMS considered placing a detector with high resolution after the first conversion of the photons, both in front of the barrel and end cap crystal calorimeters. Now, when you place them, okay, obviously this will affect the energy resolution of the calorimeter. So you have to really have to see, okay, I mean, what you gain and what you lose. And what was found out, okay, I mean, in the barrel, you lose more, okay, than you gain, but in the end cap, you gain more than you lose, okay? So you remove the barrel and pre-shower detector, and we only have an end cap pre-shower detector in the final design. So what is being done in the pre-shower detector, okay, you have a pre-shower silicon strip detector was designed for this separation, and it was placed in front of the end cap electromagnetic calorimeter. Okay, silicon wafers which has got a width of 1.8 millimeters and wide strips. These are really not micro strip, but is a mini strip detectors. You can see, okay, the strip spacing is something like 1.9 millimeters was placed after about 3 radiation lengths of lead absorbers. and the area of each wafer is something like 63 millimeters by 63 millimeters, and it covers a smaller range, okay, than the entire NCAP calorimeter is 1.85 to 2.6. And there are 4 layers, 2 layers on either side, okay, I mean, and each layer measures one direction, either X or the Y. The important thing is that, okay, I mean, we, in India, okay, I mean, some of this, about 1,000 such wafers were made in the industries here, okay, and they're assembled in the final pre-shower detector. As far as the photodetectors are concerned, again, okay, I mean, it comes from the requirement, okay, what we like to have. It need to be fast, it need to operate in magnetic field, have to be radiation hard, more in the NCAP than in the barrel, and have to have high enough again, okay, I mean, to compensate the low light output in the lead tungsten crystals, and need to be insensitive to nuclear counter effect. I'll come to what it happens, okay, when we say that. Now, for the avalanche photodiodes, okay, we need a real high gain and not so much about the radiation hardness. Okay, I mean, radiation hardness comes, but the efficiency and the noise are the more critical issues. And for that, okay, I mean, the avalanche photodiodes were the best ones. Sorry. So we used avalanche photodiodes, okay, for the barrel detector. I think we will get a much clearer picture, okay, after ATN shock, okay, we'll talk about the scintillation in the things, okay, I mean, and I think we'll have a better idea of this. For the NCAP, the main idea is that you have got a higher level of radiation, okay, so I think it has to be much more radiation hard, but you have got more energies in the NCAP. So I think the amount of amplification which you require is not as much as you need in the barrel. So it has got a moderate gain, okay, but it has to be better tolerance against radiation and temperature changes. So I think, okay, I mean, that's why, okay, I mean, 2 different types of readout were used, okay, for the barrel and NCAP. The thermal stability is maintained at the level of, you can see at the level of plus minus 0.05 degrees at 18 degrees centigrade. And so I have a thermal screen in front of the crystals, and you have to insulate a foam which decouple the crystals from the front end electronics. Okay, so that's the choice of the ECAL. When it comes to the choice of HCAL, okay, you have to first of all, honestly remember, HCAL is not the only part which measures the hadron showers. You have got something like about 1.1 interaction length, and 70% of hadrons will have their first interaction in ECAL or tracker, and shower will start there. So the HCAL in CMS needs to provide sufficient interaction length to contain the entire shower of HCAL, and one needs the following characters, okay? First of all, it has to be a fast device, okay, that is for every single device in CMS. It provides the best possible flat response, that means the possibility of linear in energy. Well, I think we did not achieve that. It has to have a moderate resolution and is to be radiation hard, particularly in the very forward region. And it is to be non-magnetic, being operated in a magnetic field. We have a mixed technologies chosen. We have a brass plate scintillator sandwich in the central part of the detector, and we have a iron with a quartz fiber inside it in the very forward region, and uses a Cherenkov radiation in that part. So we use essentially scintillation light in the barrel and the Cherenkov radiation in the forward part. So this is the HCAL layout. So you have the tracker here, you have the crystals here, then you have the barrel hadron calorimeter, the NCAP hadron calorimeter, the forward one, and you have got a layer of scintillators just outside the magnet coil, which is called the outer hadron calorimeter. So I think, okay, I mean, the barrel hadron calorimeter is, as I said, okay, these are all sampling calorimeters. Okay, this covers eta less than 1.3, and it is divided into two halves, okay, which is called HB plus and HB minus. And it is restricted on one side by the barrel, the ECAL, both barrel and end cap. And the outer side is restricted by the magnet coil, which has got a radius of 2.95 meter. Now, so within that particular thing, okay, whatever you can, whatever observers you can put in, okay, I mean, that can absorb, okay, I mean, a certain fraction of the entire hadron shower, okay, not the entire ones. And HB consists of essentially 36 identical wedges. Each half barrel has 18 wedges, okay, I mean, each wedge is 20-degree wide in phi. So, and each wedge is segmented into 4 azimuthal angles in phi sectors. So we have got 18 times 4, okay, 72 phi divisions in hadron barrel, and we have got a similar number of phi divisions in the end cap. Now, the supporting structure has to be good, okay, that's why, okay, the innermost and outermost plates of this hadron calorimeter are made out of stainless steel. Otherwise, okay, the rest of the things plates are made out of brass. So this is the hadron barrel. You can see, okay, this is a typical picture of the hadron barrel, and you have got a layer of absorber, and between the two absorbers, you have inserting a tray of scintillators. So the absorber, as I said, okay, I mean, consists of 40 millimeter thick stainless steel plate, okay, I mean, then followed by 8 layers of 50.5 millimeter thick brass plates, and then 6 layers of 56.5 millimeter thick brass plates, and finally a 75 millimeter thick stainless steel backplate. So the active material, as I said, okay, are made out of plastic scintillators. The one which is at the lowest, closest to the interaction point, and one which is the farthest at the interaction point, they are all 9 millimeter thick, and all the rest are 3.7 millimeter thick. The front layer of scintillator is a special bicron plate which produces 20% more light. Okay, I mean, one thought of this mainly because, okay, you have got lots of showers produced in the ECAL, okay, I mean, and you try to weight the energy in the first layer more. But unfortunately, when we have the final design of the HCAL which was made, okay, we didn't have enough money, okay, to read out the front layer separately, okay, and we try to combine, okay, I mean, all the 17 layers and have one, what you call a tower, which is reading out a given value of I-eta and I-phi. And to do that, okay, and we have to make that, we have to put a neutral density filter, okay, in front of the that. And now I think we are in a better situation, and which we have removed them. Inside this scintillators, we have a wavelength shifting fibers, which collect the light, and then obviously, okay, we do not have the wavelength shifting fiber cannot go all the way up to the readout board, okay, so we have to it has to be fused with a clear fiber, and then the clear fibers goes to the readout system. For the end cap, okay, I mean, it again, okay, uses similar technologies. It is a sampling device between 1.3 and 3.0, and it is supported on the pole piece of the magnet at between about 3.9 meters to 5.5 meters, okay, from the interaction point. And the plates are bolted together in a staggered geometry, okay, and this is a very nice engineering concept, okay, which came from one of the engineers, okay, from the Russian group. And the observer essentially consists of 79 millimeter thick brass plates and 9 millimeter with 9 millimeter gas for the scintillators. And there are 18 scintillator layers, unlike 17 layers, okay, in the barrel. And as I said, okay, I mean, the front one is 9 millimeter thick scintillator plate, and the rest are all 3.7 millimeter thick. The light collection is extremely similar. Now, now come the outer hadron calorimeter, and this essentially contains the entire the end of the shower, and particularly true. I mean, this is for small values of itas. Iota very close in what you call in the so-called ring zero of the calorimeter. I mean, the total interaction length is less than 6. So obviously, and if you require something like interaction length more than 9 or 10, so I think obviously you have to add some readout system, to absorb the entire hadron calorimeter before the punch throughs, go to the muon system. So we have 2 layers of scintillators. They're all 1 centimeter thick scintillators. And we have got in the central ring, we have got 2 layers of scintillators at 3.8 and 4.1 meter distance, from the interaction point. And all the other rings, we have got only a single scintillator there, at about 4.1 meters away from the interaction points. As I said, this follows the phi structure of the muon system, which has got 12 phi sectors, and obviously, we have to have the gap. It has to match the barrel. That it has to match the each contains about each phi sector has got 6 slices of the things, so that it has got 72 phi slices, and you have got the delta phi, which is the same between the barrel and the outer calorimeter. In the forward system, you have got a much higher radiation, and obviously, most of the scintillation system will not work. So we have to revert to something which is much more robust. And what is being done is that we have put in, in the very forward direction, and a steel absorber, and in the steel absorber we put in, quartz fiber. There are 18 steel wedges, which is there along the phi direction on either side of the interaction point, and there are covering. Radial coverage is 125 millimeter to 1570 millimeters, and the quartz fibers are put in. Either covering the entire length of the thing, or starting 22 centimeters away from the thing. So apparently, the electromagnetic showers will die out. After about 24-25 centimeters. From the thing. So the long fibers will see the entire shower, whereas the short fibers will only see the hadronic component of the shower. So I think utilizing that, we can try to estimate the electromagnetic energy and the hadronic energy separately. So that was the whole idea for the design of the forward hadron calorimeter. The thing is, now I think a calorimeter cannot be complete without the readout systems. So for the HCal readout, HB, HO, which uses very similar technologies. They are emitting, they're utilizing plastic scintillators, and the WLS fibers really re-emits the light in the green region. So obviously we try to have something which is sensitive to that and amplify that. And the best solution when the calorimeter which was designed was this hybrid photodiodes. And I'll say, why they are replaced later on, with silicon photomultiplier. I'll come to that later on. The fibers which were coming out, they come to, for the individual layers, they come out to something which is called optical decoding unit, where they're grouped into, for example, if you want to combine the 17 layers, all of them are grouped together, and then you try to have one such thing, which is going to the a given HPT pixel. The analog signal from the HPT PMT is converted into a digital thing by a charge integrated encoder, and the CMS QIE has two independent input amplifiers, so that it can accept and amplify the negative HPT pulses as well as positive pulses from the PMTs used in HF. Okay, so I think, okay, I mean, we have a unique design, okay, for the QIE. Okay, obviously, okay, these are replaced by new designs of QIE, and you may hear about it in some later lectures. Now, if you really look at the response in the calorimeter, okay, I mean, you first of all, we expect, okay, I mean, the calorimeters has to have a linearity with energy. Now, this is satisfied to a large extent in the electromagnetic calorimeter for electrons and photons. The thing is, okay, the only thing which really comes in the way, okay, for the nonlinearity is the so-called the effect of the quenching, effect of the non-uniformity in the crystals, and also the saturation of the shower leakage. But that is a small fraction, okay, but we obviously, okay, we have that more or less satisfied. But in the case of hadron showers, the non-electromagnetic part of the shower has an invisible energy component, and the fraction of the non-electromagnetic part depends on the incident energy. So one way to bring back linearity is to have the response ratio of electrons and pions to be the same. But unfortunately, this we cannot have. CMS has two calorimeters with totally different E over pi. For the crystal calorimeter, it is 4, and for the brass scintillator, it is about 1.4. Okay, I mean, this is verified in a number of test beam activities, and obviously we cannot have totally linear things, and we have to rely on something else. Okay, I mean, some software compensation, okay, I mean, for our what you call the particle flow method to achieve this. Now, this is from the very early days of the signal, and the reason for doing that, okay, I mean, showing these pictures is to see that how well we understand the detectors, okay, from the very beginning, okay, I mean, and this is the signals of resolutions of the electrons in the barrel and end cap, and you can see the black point is the data, and the histograms are the Monte Carlo. So this is the electromagnetic calorimeter. This is the missing transverse energy in the entire detector, and this is the response of the combined calorimeter as a function of the track momentum. Okay, so I think in every places, okay, when we have a fairly good agreement between data and Monte Carlo, and I say, okay, I mean, we understood the behavior of the calorimeter, okay, I mean, from the very beginning, but we had some surprises, okay. And the first surprise, I think I show the two surprises, okay. I mean, one of the surprises we saw that we are measuring the energies in the electromagnetic calorimeter, and we cannot really explain the energies in the calorimeter, which is the black points, with our best knowledge of the simulation. So this is one thing. Okay, the second thing was that, okay, we have events with a large transverse energy, missing transverse energies, and our simulation does not tell us, okay, that we have these things, and are they discoveries of new physics, or they are really some background? So we have these things, okay, which we have from the beginning, and we slowly understood, okay, what are the possibilities. First of all, when we see these particular things in the ecal crystal, okay, I mean, we saw that we only see them in the barrel part of the detector and not in the end cap part of the detector. That is number one. Secondly, we see that it happens in a single crystal. When an electromagnetic shower happens, okay, electromagnetic shower usually happens in several crystals surrounding a central crystal, but this happens in a single crystal. And unfortunately, though at the beginning we had two APDs which are attached to the at the end of a crystal, again, for the cost of the readout, okay, I mean, we combine them, okay, we do not have an idea, okay, I mean, if it's coming from one APD or the other, okay, so we are dark about that as well. And the other thing which we saw is that the time of this pulse is consistent with the instantaneous signal from the APD, not the typical decay spectrum. Okay, I mean, if you look at the decay spectrum, I think it is always, okay, I mean, happens in the front part, okay, not in the decay spectrum. And the rate of the spike of the events is is approximately 1 per what do you call it? 1,000, 1 per 1,000 million bars events. Okay. So I think, okay, there were a working group which was set up, okay, whenever we have problems. So similarly, a working group was set up, and we try to see, okay, that first of all, the spikes happen only during collision data, not noticed during the cosmic ray runs spanning the previous years. The rate was roughly proportional to the minimum bias rate. And the thing is, okay, there were an extensive beam test which was performed prior to that, and they were not observed whenever the beam tests were done with the electron beams. Whenever there was a combined calorimeter runs, we saw some cases, okay, of high energy deposits, I think, which were roughly, I would say, I mean, it was to some extent ignored, okay, I mean, before the real collision took place. So most likely, I mean, all these observations, okay, came up to the idea, most likely the spikes were produced by showers of particles like other energy depositions in the calorimeter. A simulation study demonstrated that the spike was due to the DDX loss of hadrons, very low energy hadrons in the APD, and most likely these low energy hadrons are produced in the epoxy layer, which is just preceding the thin high multiplication silicon layers of the APD. So obviously, okay, I mean, when that thing is done in the simulation, we have a perfect agreement. And there are other ways, okay, of this removing those things, okay, which was done both at the level of the trigger as well as the level of the readout. So I think, okay, I mean, we understood this thing in early 2010. It is 2010, yeah, it's 2010, and then I think we have forgotten about it. Now, that is about the ECAL. What about HCAL? All HPDs were tested in the context of magnetic field, but these tests were done in a uniform magnetic field with field direction along z-axis. Now, we had what we call a magnet test and computing challenge, okay, which was called a MTCC, okay, I mean, just before the run. And at that time, okay, I mean, we found out, okay, that we have some problems. Now, this particular thing is good for the barrel and end cap where the HPDs are placed inside the magnet coil. But HOs are placed outside the magnet coils, and the B field is due to the return yoke where there is a substantial radial component. So obviously, okay, I mean, whenever you saw this thing, okay, I mean, we tried to what happened? Whenever we try to find out a place where the field is tolerable and we can place them. Okay, so that was the thing which was taken as a first step because we had no other alternative at that time but soon we try to see that if we can replace HPDs with something else, and that's why, okay, I mean, we had a very early days, okay, we have to introduce the silicon photomultipliers in HO. And in fact, okay, I mean, HO was a testing ground of silicon photomultipliers in HCAL.
Not in HCAL, I think all over the world.
Now, I think HPDs also had problems for parallel end cap detector, and we saw substantial noise in the readout from the both HPs and HEs, and we saw the periodicity of this particular noise. Okay, I mean, and we saw there are three types of periodicity. For the first periodicity, that it happens in the individual, it is a how much noise is there, okay, in individual channel, okay, so one channel is there, and this is essentially due to the so-called ion feedback. That means the photoelectrons induce liberation of ions from the silicon diode, which accelerate, okay, I mean, across the high voltage gap and produce again electrons and ions in the photocathode. So that gives rise to the so-called feedback. The second thing is, see that, okay, I mean, we have signals in a block of 18 thing, okay, which is makes one part of the what do you call one phi sector. So with the HPDs operating at 8 voltage and with the magnetic field from the wall can produce large signals, and this is the so-called the HPD discharge. And the third thing happens for the entire thing, okay, which is called the RBX noise. It happens for the entire 72 channels in a readout box. We do not fully understand, okay, for these readout boxes, and but introducing SIPMs, these two things are gone, okay, and we still have to deal with this, but we have on the offline, we have filters, okay, which can takes care of this. We also have issues in the HF, and we see this high energy tails in the HF. And this we, again, okay, I mean, we have a hint, okay, of this particular noise during your test beam. We saw when you're hitting in the test beam with a muon system, we suddenly saw, okay, I mean, a huge energy in the HF. And then we saw, okay, I mean, there's a photomultipliers which is behind the HF, and in the real HF as well as in the test beam. And we saw that whenever we have this particular thing, okay, I mean, we see that this photomultipliers are lit up. That means, okay, some of these particles, okay, high energetic particles hitting the photomultiplier windows, okay, and then they produce Cherenkov light there, and that light, okay, produces a signal. So I think obviously, okay, we have to, again, okay, we have one photomultiplier tube for each readout channel. So obviously, okay, I mean, if you have multiple photomultiplier tubes, okay, for a given readout channel, we can eliminate that, but we didn't have that, okay, at the beginning. So we had to do it by some means in the software, but soon we try to replace that in the readout system with a multi-anode photomultiplier. Okay, so this is not only photomultiplier which causes this. Okay, I mean, we also produces light, okay, in the fibers of which comes behind the absorber, and if some stray light which comes in, okay, I mean, it can produce also the signals in the HF. Okay, and so I think, okay, when we have at least in our simulation, we have also tried to simulate that, and that explains, okay, our all these issues. Okay, I mean, we can explain everything, okay, with that. And in fact, okay, we have taken on the hardware side, okay, how to take care of this. Now comes what happens as a function of time.
8 to 9 millimeters.
Okay. One of the things which we saw, okay, from the very beginning, that none of our detectors, okay, I mean, will be doing exactly the same with this high radiation level of LHC. And if one tries to look at the behavior of the CMS ECAL, you can see, okay, I mean, this comes from some sort of a model studies, okay, at the very beginning, that depending on where that particular ECAL is, okay, I mean, the light collection efficiency will drop by several orders of magnitude. And this we knew, okay, at the very beginning. But I think, okay, what we saw in reality is that we saw this was a little bit optimistic, okay. I mean, we saw even harder radiation damage, okay, in some of the N-cap crystals. So obviously, okay, I mean, we need to replace, okay, I mean, there's no point of keeping a dark crystal in the detector. We have to replace it by some means, okay, particularly in the N-cap. So it's not just in the ECAL, we see a similar thing for the hadron calorimeter itself. In the hadron calorimeter also sees the aging effect, and it is almost dying, okay, as a function of time. So what we try to do? We try to replace the entire N-cap calorimeter, both electromagnetic and hadronic, by something which is much more radiation hard, and we utilize the so-called silicon technologies at a very, very high radiation level. And when the radiation level is not so high, we can come back and having scintillators as well. So this is our design of what we call a high granularity calorimeter. So you have got a total of 47 layers of detectors. 26 of them are in the electromagnetic sections and 21 of them in the hadronic sections. In the 26 of them, okay, they have got essentially the main absorber is a copper tungsten plates, and in the hadronic section, the main absorber is iron absorbers. And it is called high granularity because we try to put in a large number of detection channels. You can see, okay, we have got something like about 6.5 million detector channels, which will also act as a tracking calorimeter. So it is it's not just a calorimeter, it's also a tracking device. Okay, so it can try to identify single tracks, okay, inside this calorimeter system. And this is a test beam structure for doing that. And you can see, okay, I mean, in a given layer, okay, we have got absorbers with you have got absorbers with silicon layers on either side, okay, and then you have a this is a cooling plate with the silicon layers on either side, and then there is an absorber after that. So this went through a test beam thing, okay, and this was a picture of the test beam which happened in October 2018, where several layers of this absorbers were put in. And I think we had got almost all layers of the electromagnetic and some layers of the hadronic. And then there was a detector which was borrowed from Calis, which is called HCAL, which is a scintillator detector, okay, which is tries to cover the entire things. And utilizing that, we found out, okay, we got a good resolution, and particularly we had a much better resolution when we tried to utilize not just a standard way of calibration, but using, say, deep neural network. And you can see from using this study, okay, which was done by Alpona here, she could demonstrate that, okay, the resolution drops by almost by a factor of 2. And the detector is very linear, okay, as a function of energy. So we have retained linearity. We have a very good resolutions for the hadronic component. Of course, okay, the electromagnetic component cannot be as good as a homogeneous detector, but it is pretty good. Now, let me just go to something, okay, I mean, which is still is debatable. That means, are we good in the very forward direction or not? In very forward direction also, you can see that we have got a quartz calorimeter, but even in a quartz calorimeter, if you in run 3, okay, I mean, you see you have a substantial decrease, okay, of the light collection as a function of eta. And if you go to end of run 3 to end of run 4, okay, I mean, and particularly when you go to even run 5, I think the HF, particularly at a very small eta, will be like EE, okay, at the end of run 2. So I think, okay, I mean, there have been several types of things which has been thought about, and I'm just focusing on only one of them, to have something like an HGCal, okay, which is with not as sophisticated as HGCal, but with only 6 layers in the electromagnetic section and 2 layers in the hadronic sections, and covering, okay, I mean, something like I mean, it goes from eta 4.5 to up to going down to eta 4.5, and the thing is, okay, I mean, it gives, in addition, okay, the 10 lambdas of the quartz fiber calorimeter behind it, okay, I mean, it will be give a very good energy and determination, as well as the time determination. And you can see, okay, I mean, with and without this particular thing, okay, I mean, how well, okay, I mean, you can gain in resolutions, okay, from for both the electromagnetic section as well as for the hadronic sections. So the very forward direction is very important, okay, I mean, when it goes to this run 5, even in run 4. So such a thing may be worthwhile considering, okay, I mean, and I think, okay, there is a group of people who are trying to consider, okay, I mean, if such a thing can happen. So I come to my end, okay, I mean, just to summarize that calorimeters are essential in high energy physics experiments of today. There are lots of R&D activity takes place to design an acceptable calorimeter for a given application. Physics priorities in an experiment drive the final choice of technology. Even after, this is the lesson at least I have learned, even after all the preliminary work, the real application gives surprises in the real life applications. So one really has to watch out whenever you try to have a very well designed calorimeter, well tested calorimeter in the real application. And you may find out, okay, what type of problems you face, and you have to try to solve it online. So the next generation calorimetry employ new techniques. It employs the dual readout. It employs the high granularity and maybe a few more, okay, on the hardware side. It employs the particle flow, artificial intelligence on the software side. Thank you.
Okay, I hope you had an excellent overview of this calorimeter and the experience of running of this calorimeter. So I just add one more point on this. He said that calorimeter, but I think in the most of the experiment what you design and the simulation you do, when the real data come, there is always a surprise. And for that, usually you call this real detectors, ideal detector simulation and real detector simulation. This is when the data comes, it's really a surprise. Yeah, now any question? Professor Banerjee? Okay. If not, then I think Sunanda, thank you again. And the place of the experiment, I will again the present similar thing to what I did to the all others. This is the collection of our TIFR collection. You have seen it. And this is one of the three. Thank you.